Today we're going to be talking about how we can improve our ability to estimate vital rates of endangered fish on the San Juan River using novel applications of pit tag technology. First, I'll kind of introduce some of the issues and then the objectives of our study, and I'll talk about the background of the area and some of the technology, and then we'll discuss the methods and the implications of this research. Biodiversity is severely threatened worldwide, and most of us are aware of these endangered animals because they're large and charismatic. However, freshwater species are in the greatest rate of decline, with up to 39% of freshwater fish that are described in North America being considered imperiled. And this has led to an urgent need for conservation strategies. And not only are the fish endangered, but the habitats in which they live are also threatened. The Colorado River Basin, for example, was voted the most endangered American river in 2013. It flows through 7 different states and 2 countries. It is relied upon by 30 million people for just drinking water alone, and it's dammed and dewatered along the entire course of the river. And this is somewhat of a problem for desert fishes. They compete with humans for this water. Most are non-sport species, and they're characterized as being of no economic worth and non-charismatic. And this leads to many of these desert fishes becoming endangered. The threats facing these fish include habitat degradation, the introduction of non-native species, altered flow regimes, and human water use. And these are 4 of the species on the Colorado River that are endangered: the bony tail up here, the humpback chub, the Colorado pike minnow, and then the razorback sucker. They have evolved over time in the Colorado River system to respond to drought cycles with their very long life histories, and then they've also evolved unique morphologies to deal with the flow rates that they have to deal with. And it's led to a very specialized assemblage of fishes that are also incredibly imperiled. And when you have imperiled fish, the idea is to increase your abundance to a desired level to meet some sort of recovery goal. And once you get to that abundance, you try to maintain those population numbers for at least 5 years. And you need robust estimates of survival, abundance, and population growth in order to determine this. Which leads to some very basic population dynamics questions, such as how many are there, which we answer with abundance estimates, and how is that population changing over time, which we answer with survival rates and mortality rates. The way that we go about getting some of this information currently for fish involves electrofishing on these rivers and mark recapture studies. And the way the mark recapture studies work is we go out and have a sampling event and capture as many fish as possible and mark them with either a tag or a fin clip and then release them back into the system. Then we go back for a second event and look at what we have, and the ratios of marked to unmarked fish go into our estimators and produce an abundance estimate or survival rate estimate. And the problem being that if you have low recapture rates, you get poor estimates of abundance with huge errors. Some of the problems that we have with these methods is that, first of all, they're endangered fish, and we're shocking them, which has been shown to have negative impacts on their survival and reproduction. And then the problem for our estimating is that these fish are already at low abundances in very large rivers. And as you can see in this picture, sometimes those rivers look like chocolate milk. It makes them very hard to detect, and you have low recapture rates. And these efforts also include a very high cost. In just the Upper Colorado River Basin alone, annually we spend more than $10 million for these 4 fishes. And this is what we can expect to see based on that information. We have survival rate on the left over here with the effort expended to get that on the right. And as you can see, that effort increases over time, and our estimates are bad throughout. The variation is wild. It almost spans 0 to 1. Which is a horrible way to get a population estimate or an estimate of survival rate. You can't conclude anything from that. And I'll talk about the objectives of our study is to develop a field protocol for a new method of collecting resite data. And in order to do this, we have created a rule set, and we're going to validate that with a field experiment. And we're going to use that information to generate more robust estimates of these vital rates for endangered and rare fishes. And we'll compare these estimates with and without our correction, and then also look at what the cost of these different systems are. Start with the background. The San Juan River is where our study is going to take place. It is very typical of these large desert rivers. It has a main stem large dam right here, and there are diversions throughout the system that take water out for agriculture, hydropower, and urban use. And it's also representative of all the habitat types you would expect to see on these large rivers, from canyon-bound reaches to braided, broad floodplains. And the fishes that we're going to focus on are the Colorado pike minnow and the razorback sucker. The pike minnow was federally listed in 1967, and we began stocking those in 1997. And they get stocked at around 100 millimeters, and so they're not tagged initially, but once they're recaptured, we tag them and release them again. And so far, around 50,000 fish have been tagged. The razorback sucker was listed in 1991, and we began stocking in 94. They're stocked at 300 to 350 millimeters, so they get tags before they go in, and 150,000 tagged fish have been released into the system. The reasons for these fish's decline within the San Juan is very similar to a lot of other large western rivers. There's a major dam, there's a lot of diversions, and also the non-native fishes that have been introduced, the channel catfish and common carp, prey upon and compete with these species. We tag them with pit tags, which is the same technology as what you tag your dog and cat with, the microchips that they have. They are passive, which means that there is no battery, so they have a very long life and a very small size. They give our fish unique identification numbers, and they're also relatively cheap compared to, say, GPS collars for elk. They're around $2, so you can tag thousands of them at a relatively low cost. And with our market capture studies that I was talking about, this is what you end up doing. There's a hand scanner, and so you can scan the fish for the tag and know exactly which fish that you've caught and see its progress over time. The next step with the antennas in development was, or with pit tags, was the development of these antennas, which you can put in streams or diversions, and you can pair them, as in this top picture here, or in here with this paired system, to get direction based on sequential detections. Or if you have a well-mannered system like the Pacific Northwest with salmon, you can use a single antenna because you know exactly where those fish are going to be moving and at what time of year, so you just get numbers from that. Antennas have been shown to be extremely effective in increasing our estimated vital rates. In the lower Colorado River, the addition of one antenna increased our estimated rate of survival from 9% to 39%. And of the fish that were detected, 93% of them had not been seen since their initial stocking. We've taken it a step further and taken these antennas and mounted them on a raft, and also hooked it up to a GPS system so that we can go out and find the fish and not wait for them to come to our antennas. This was developed by Mark McKinstry and Peter McKinnon back in 2008 with the intention of improving the estimated vital rates. And there's a couple side benefits in that there's no harm to the fishes, and if you get weary while sampling, you can take a nap. We have certain issues with this, however, in that we detect tags and not fish because we're the thing that's moving. And so the status of the fish, we can't conclude whether it's alive or dead. We also don't get biological data such as length, weight, or growth, and so we can't calculate any sort of condition metrics. Detection distances can also be an issue if the read range of our system is exceeded by the depth of the river, but the key is that the tags are detected and not the fish. And now we'll talk about our methods. The field experiment that we designed is on the San Juan, and it starts out at the hogback diversion and goes all the way down to the Clay Hills Takeout, which is around 257 kilometers. It's the designated critical habitat of both the razorback sucker and the pike minnow. We plan on doing at least 4 to 5 passes in order to get multiple detections so that we can draw conclusions about their movement. And then we're also going to do that over the course of 2 years so that we can see the effects of spawning migrations and spring runoff. We did a pilot study in September on the San Juan. We did 3 passes on 3 days over a 16-kilometer reach from the hogback diversion down to Shiprock. And we used 1 boat, and we had a read range of just under a meter. And as you can see, we detected a lot of tags. We had 633 unique tags detected over those 3 days. This graph compares that with the shocking data from 2014 with the number of fish on the y-axis and the species on the x. Recaptures from 2014 are the blue, and our pilot study is the orange. And we got almost a third of what they did over the course of a year in 3 days with the razorback and around a quarter with the pike minnow. But we got a lot of unique tags detected, and so that we can see how that affects our estimates of survival rate. The effort that we expended is a lot less, so the rate of that decreases, and our estimate has increased because of the increased number of detections, and also our error has been significantly reduced due to that increased number of detections. But we still don't know if they're alive or dead, so we plug that into the rule set that we created, and the first rule is based on the distance moved. If they move less than 10 meters, then they're considered unknown, and we'll look at the movement between years to get at more with that. And if it moves 10 meters or more, then they're considered to be likely alive. This graph shows the frequency of movement on the Y and the distance moved on the X. And I don't know if you can see or not, but down here it shows that they've moved up to 1,500 meters in a day. And these on the right are considered to be likely alive. The next rule is based on the direction moved relative to flow. If they move upstream, then they're considered alive and confirmed that way. If they don't, then we move on to our next rule, which is based on having at least 3 detections. And this rule is based on the movement of direction in between detections. And so if there's a reversal of bearing, as in it starts here, goes here, and then comes back to this one, then it's confirmed alive. And if there's no reversal, it's still considered alive based on its distance moved, but it's not confirmed. And then the movement between years, if it moves less than 10 meters, we consider it to be likely dead. We expect runoff or spawning migration to make them move at least 10 meters. And then if it moves 10 meters or more, we kind of start over. And with our preliminary results from that pilot study, we had 186 that had more than one sighting. 92 of those were considered alive, and 42 of those were confirmed alive by multiple rules. And 94 were unknown and possibly dead. But we also had a handful that we had not seen with any sort of sampling since 2006. And another way that we're going to make our rules better is with the addition of known dead tags and known live. The dead will be based on us seeding the river with bear tags to simulate the movement of these tags. And then the known live, we're going to match our detections with electrofishing data and the antennas that are already within the river. And this is what we can expect from that. The estimate drops with the application of our rules because there are less live fish in the system, and our effort, the rate is still increasing at a much slower rate. The error bars maintain about the same. And then with knowing which ones are dead and which ones are alive, we can also censor the data set and get rid of the dead tags within the sample set, and that also decreases our estimate, but our error is maintained about the same. We can also do this sort of thing with abundance, but we're not entirely sure how that's going to respond with regard to the variation. And this shows the efficiency of our system versus the traditional methods with catch per unit effort on the y-axis and the species on the x. 2014 data is again in blue and the pilot study in orange. And as you can see, we had about 3 times the efficiency with the razorback sucker and about double with the pike minnow. And now I'll talk a little bit about the implications. The future management of endangered species relies on understanding the effects of management actions on these populations. And with the much better estimates of survival rate, we can get at how management actions are really affecting them. And this could in turn lead to changes in our conservation efforts. And our high efficiency could also free up some resources to do other things to help these fish through habitat restoration or whatever else is necessary. And then we also expect to see a dramatic improvement in the accuracy and precision of our estimates, and we'll be much more certain about the population status moving forward. And we could also see healthier fish due to the reduction in number of shocking events. And we could also identify habitat use based on the location data that we've collected with this system. And I'd like to thank Peter McKinnon, Mark McKinstry, my committee member, PBQ, and everyone else that's helped with this presentation and the collection of all the data. Questions?
Please.
Just a technical question. So it looked like your array was, what did you say, 6 or 7 meters long?
Around 9, actually.
So how do you nail things down to a distance moved of 10 meters? It seems like just the size of the rig makes that difficult.
Right, but so the GPS system is based on one particular spot in the middle. And so out to the edges of the antenna, you only have 4.5, 5 meters. And so that 10 meters is still about double of what that error would produce. Does that answer your
I
question?
mean, well, I mean, if it moved from one end of the array to the other side of the array,
Yeah. And so
you
that
still
10
have it
meters-
in the same spot, right?
Yeah, and so the 10 meters is still somewhat of an arbitrary number. Like as we get like the movement of known fish and known dead, that will be modified as we move along.
Well, Wayne, are you asking how you figured out 1,500 meters?
No.
Okay.
The criteria was a movement of 10 meters.
Yeah.
The fish could move 9 meters and still be
Yeah.
detected in the, you would say it's exactly the same spot. So
Right.
there's some swapping.
Yeah, and that's something that we're working on.
So how are you gonna account for the difference between dead and shed tags?
We're not trying to, I guess. If the fish dies, our passes are gonna have at least like 2-3 weeks between. We'd expect that they'd fall out of that fish due to decomposition in that time. And so we're hoping to just model the bear tags. We considered stocking like a dead fish with a tag in it just to see what that does, but we've gone the other way with that and decided not to do it.
It's possible a dead fish would still move, right?
Yes.
And then the tag might be shed somewhere else. So some of those that have moved might also have probably there.
Yes. And we're hoping to see as we detect that fish more and more times, like after that tag drops out, that we can pull that out as well. Ed?
This might be totally irrelevant, and feel free to tell me so. But you showed on that, in 3 days, you got a third and a quarter of the amount of fish detected they did in the entire season beforehand. Have you worked out what a cost saving would be generated if you were to catch the same number of fish as they did using your technique?
No, but the cost between the different systems is something that we're going to get into for sure.
Might be worth doing that for selling it.
Yeah.
Thanks a lot, man.